Hey, we're going to look at solving separable differential equations in this lesson. And if you want to print the sheet that has the fill in the blank notes and the examples I'm going to work, you can go to that bit.ly link. Separable DE, S, D, and E are capitalized. And on we go. So let's talk about what separable differential equations are. And there are a lot more types of differential equations that can be solved, yet in AP Calculus, we only focus on solving those that are under the separable differential equations category. And a separable differential equation is any equation that can be written in the form dy dx is some function of x times some function of y. If you're adding x to y, that's not separable. It must be f of x times g of y. And that's really the only one you need. I decided to add a couple more here that are the same type thing, but with a slight different appearance. One of them is f of x divided by g of y. The other was g of y divided by f of x. But those can be very easily written in the f of x times g of y format by simply changing 1 over g of y to changing it to that 1 over g of y times f of x. And similarly, 1 over f of x times g of y. I really blitzed through those second two, but do keep in mind that you want it to be f of x times g of y. And then it is in what we call the separable category. And so after you get it into that form, if you are in the form dy dx is f of x times g of y, once you're in that form, then we have a set of procedures, which I'm not huge on memorizing just a list of procedures to go through, but this is one of those few things in calculus that does have a general flow on how to solve the equations, the differential equation. And in all these examples, I'm assuming we have like dy dx. It's not like a dp dt situation. So we're dealing with y's and x's here. And step number one is to separate the variables using algebra. And the majority of this process is algebra. As a matter of fact, I'm going to put a star next to every step that is algebra. And you simply move everything with a y to one side of the equation, everything with an x to the other side of the equation. And that is what we call separating the variables. And after the separation step, your equation should be in the form g of y times dy equals f of x times dx. So you separate all of the x's and y's. Then we move on to the next step, which is your integration step, and you simply find the antiderivative of each side of the equation after you get it separated, of course. And with any antiderivative, don't forget there is a constant of integration that must be included, so don't forget that plus c. And from that point forward, plus c is a permanent fixture of the problem. You must have a timely c. It must show up in that integration step. You can't do the antiderivative, then do a couple more steps of algebra, and then put the plus c in. So make sure that that plus c is showing up the instant you find an antiderivative. Then after that, we have two more steps of algebra. Both of these are algebra, and because they are both under the algebra heading, you can actually do these in either order. You can do step 3 before 4, or you can do 4 before 3. They are both algebra. I personally prefer to solve for your constant first, and that is if you are given some initial condition. So if they tell you that the solution passes through the point 1, 3, then you can use that ordered pair to solve for the constant, and I'll show you an example of that in a minute. And then after that, you want to solve for y, because in these problems, they always ask you to write the solution in the form y equals f of x. This is really what you want. And so you should be finishing in the form y equals h of x. And I just now noticed, and I did this twice with my classes today, and I didn't catch this, the f of x here is not the same as the f of x I have here. So I think I'm going to come up here, and I'm going to change this to an h. I don't want you to think that that the equation you end up with for the solution is the same one that you originally had times the dx in the separation step. So slight little notation mistake right there. And let's go on and look at a few examples. I'm going to skip number 1. I'm going to come back and do that one second, actually, because I think number 2 is a better example to do first. So we have this differential equation, dy dx is xy squared. And in your separation step, if you need to do this in baby steps until you're super comfortable with it, I'm going to rewrite it here to make this easier to see. First, start by making sure that you are in separable form. You are in that f of x times g of y format, and we are. It is a function of x times a function of y. The function of y is y squared, so we do have the correct format. Now I am ready for separation, and you can start by separating the dy from the dx by multiplying both sides of the equation by the dx. That gives me an equation of dy equals xy squared dx. So all of my x's are together, but the problem is there's still a y squared smack dab in the middle of it all. So I will divide by the y squared, divide by the y squared. And now I have a fully separated differential equation of dy over y squared equals x dx. And once you finish that separation step, we are now in the world of antiderivatives. This is the only calculus step in this process. So we will integrate, find the antiderivatives of both sides of the equation. I'm going to start with the right side because it's a little bit easier. The antiderivative of x is x squared over 2. Don't forget your plus c. Put that plus c. The instant you do an antiderivative, there's your plus c. Don't leave it out. Dy over y squared. If you want to go to scratch paper, you can. That will be y to the negative 2 dy, and the antiderivative of that is from a power rule, add 1 divided by the new exponent, y to the negative 1 over negative 1, which is the same thing as negative 1 over y. And I'm going to write that over here. And for just this one time, I am also going to include a constant on the left side because I did do an antiderivative of y. Therefore, I should put a plus c. However, be careful, because if you put plus c, you might be tempted to combine those constants and subtract them out completely and just throw it away. You don't want to do that. So to appease the gods of math, what you should do is do something to designate that these two constants might be different. You could call one c and one d. A standard convention is to call one c1 and the other one c2. But I'm not even going to do that because if both of these are constants, I could subtract this C2 from the other constant over here. And if I have an unknown a constant of unknown quantity, I don't know what C1 is, and I subtract an unknown quantity from it, I'm left with just some other constant that I don't know. And so what I will do, instead of putting a plus C on both sides, I will only put a plus C on the right side with my x's or the independent variable, and that will serve as the constant for both. And so I will no longer put a plus c on both sides until we've done the antiderivative. Now we have two more steps of algebra. I need to solve for c, and then I ultimately need to solve for y, and it is a little bit easier. Usually, there are some exceptions, easier to solve for c first. So if f of 2 is equal to 1, then I know that negative 1 over y, which would be negative 1 over 1, is x squared, which is 2 squared over 2 plus c. And when you solve that for c, you will find out that c is negative 3. Once you solve for your c, you put it back into the equation that you solved, that you plugged the initial condition into. So I'll reset my solution to negative 1 over y equals x squared over 2 plus minus 3. And we have one last tiny step, and that is to solve for y. And there are a couple of things you can do to solve for y. I think the first thing I'm going to do is move that negative over. So 1 over y would be negative x squared over 2 minus 3. And there are a couple of things you can do to solve this one. What I like to do, I do not like my y being on the bottom. So what I actually can do is I can just flip the left side. I can basically raise the left side to the negative 1 power, which makes it y over 1. But if I flip the left side, I will need to flip the right side. And if you use this method, just make sure you flip that right side in its entirety. And that will give me 1 over negative x squared over 2 minus 3. And that should be a plus 3. I knew something was wrong. When I move that negative over, that should be a plus 3. All right, there we go. Whoops. Okay. That is an acceptable answer. If this is a free response question on the AP exam, if you're an AP Calculus student, that would be acceptable. However, if this were a multiple choice question, they very well may not have it like this, and they probably wouldn't. So I'm going to get rid of that over 2 in the denominator here by multiplying the denominator by 2. But if I multiply the denominator by 2, I must do the same to the numerator. And I finally have a solution of 2 over negative x squared plus 6. And I'm going to leave this one like that. So they're kind of lengthy problems, a lot of algebra, a lot of manipulations, but separate, find the antiderivative, and then do a few more algebra steps, and you're good. So I'm going to move on to number 1. And for number 1, dy dx is equal to x divided by y. And again, if you want to go in baby steps, you can separate the dy from the dx first and have dy is equal to x over y dx. But I have a y in the denominator over there. I need to fix that. So how about I multiply both sides by y? And if I multiply both sides by y, they will divide out over here on the right side, leaving me with y dy is x dx, and that is our separated equation. We are ready for antiderivatives. Antiderivative, antiderivative, and these are both very nice. Y2 over 2 equals y2. Y squared over 2, x squared divided by 2. Don't forget your constant. And again, the constant on the right side with that independent variable of x is sufficient for both of the antiderivatives. And so I have that solution, but I now have two steps of algebra. I need to solve for c and I need to solve for y. But before I just dive straight in to plugging in my initial condition, I'm always on the lookout for things I can do to make this problem a little bit nicer. And for this one, if I multiply the entire equation by 2, I end up with fewer fractions. This is nice. So I have y squared is equal to x squared. And you could call that plus 2c. 2 times c would be 2c. But again, I don't know what c is. If I take an unknown quantity and I double it, I still have an unknown quantity. So I can put a c there that still represents some unknown constant. However, again, to appease the gods of math would like for you to put something here to indicate that this constant is a different constant than the previous step. Now, that is being true to the rules of mathematics. That said, on the AP Calculus exam, again, if you are an AP student, they won't care if you just put a plus, if you just keep that as a C. As long as in the end your solution works out, you'll be fine. So I'm going to go with y squared equals x squared plus c. Now I'm going to solve for that initial condition, or solve for the constant using the initial condition. F of 0 is 3. So that'll be 3 squared is equal to 0 squared plus c. C is 9. And once you solve for the constant, you can reset the equation that you used in solving for the constant. Y squared is x squared plus 9. And then this one's a lot more convenient to solve. I just simply square root both sides. But don't forget, if you create the square root, you must remember that y could be the positive or the negative root of x squared plus 9. So technically, at the moment, we have two solutions. We have y equals the root of x squared plus 9, and we have y equals negative root x squared plus 9. Yeah? But we can't have two solutions. The instructions are, and this is pretty standard, find the particular solution, not find several particular solutions. And so we have to decide, should I keep the positive root or should I keep the negative root? And to figure that out, you simply look at the initial condition. My initial condition is positive. When I plug in 0 for x, I should return a positive 3, which means I'm going to go with this one, not the negative root. But it does need to be a conscious thought, because all they have to do is say f of 0 is negative 3, and then you have to keep the negative one and you throw the positive one away. And that's not uncommon. You'll have to do that again. I would bet money. So let's go on looking at number 3 here. And I'm going to have to pause this. I'll come back and finish this one in just a second. Okay, so let's look at 3 now, and I have my 5-year-old son in the room with me, so hopefully I can get through this without any interruptions. So if you look at number 3, on the surface, it may not look like it's in separable form. Well, it's not in separable form right now, but it may look like it's not a separable differential equation, because you do have xy plus y, and I did stress that it must be a function of y times a function of x, but there are times where before you start the separation, you just have to do a tiny bit of algebra. And that's what's happening on number 3 here. And so I have xy plus y. I will factor the y out. And when I do that, I have y times x plus 1. And we magically are now in a separable differential equation. And I would like, at least for my students, to get to a point where they do all of their separation in one big step, where they're not multiplying by dx and then moving whatever else over. I do know that I want to multiply by the dx. So I'll have x plus 1 dx on the right side, and I need to divide by the y to move it over. So I have dy divided by y, and in that one step, we are now separated. So do it in one step instead of 2 or 3 if you can. Just expedite the process some. Let's find antiderivatives. And so my antiderivative of the right side is pretty convenient, x squared over 2 plus x plus c. Left side, dy over y. If you don't like dy in the numerator, then just kind of go off on scratch paper, write it as 1 over y dy, and you should know that that is the derivative of the natural log of y. And so there is our solution. As far as the antiderivative step, now we need to solve for c and solve for y. And I'm going to solve for c using the initial condition, f of 0 is 5. And if I know that f of 0 is 5, then I would have the natural log of the absolute value of 5, which is just 5, is equal to 0 squared over 2 plus 0 plus c. And so there's my c. I can now reset my equation. Natural log of y is equal to x squared over 2 plus x plus c, plus the natural log of 5, plus the natural log of 5. And then I need to undo the natural log, and that is done by e-ifying the problem, or exponentiating. Make both sides exponents on e, and we now have the absolute value of y is equal to e to the x squared over 2 plus x plus the natural log of 5. But then we have to tackle the absolute values. How in the world do we tackle the absolute values? And we'll think of that. Let's just think back to like algebra 1. We'll shrink this up so we can see all of it a little bit better. It shrunk it up. In algebra 1, if I told you that the absolute value of a number could be, I don't know, 7, well, hopefully you knew that that meant x could be 7 or x could be negative 7. And it's the same thing here, kind of like the plus or minus with the square root problem we did a minute ago. If absolute y is equal to all of that, then I know that y could be just that stuff, e to the x squared over 2 plus x plus the natural log of 5. Or perhaps y is the negative of that, e to the x squared over 2 plus x plus natural log of 5. And just like the other problem, to determine if I keep the positive or the negative, we look at my initial condition, and this initial condition is positive. When I plug in 0 for x, I should get a positive result for the y coordinate. And because of that, I know that I want to keep y equals e to the x squared over 2 plus x plus the natural log of 5. That can be written in a slightly different way, but I'm already at 17 minutes, so I'm going to leave the answer looking like that, and we will go on to number 4. And this one's a little bit cleaner. dy dx is 4y. So with this one, separating is going to be pretty nice. Now, when you're separating, I wrote this problem very specifically to make one point. When you're separating your dx from your dy, and I think I will do this one in baby steps, when you move your stuff over to the y side, I try to keep my y side as clean as possible. I don't want to move too many things over to the y side, because eventually I'm going to have to move it back over when I solve for y later. And so while I could divide by the 4y, it's a lot better to divide only by the y and leave the 4 on the right side. And so I have dy over y equals 4x dx. And now we have antiderivatives. It's going to be similar to the last problem. And so dy over y, that is the derivative of the natural log of y. 4x's antiderivative would be 2x squared plus c. I'm going to use my initial condition. F of 1 is 5. So if f of 1 is 5, that means the natural log of 5 is equal to 2 times 1 squared plus c. Kind of ugly c, but natural log of 5 minus 2 is equal to c. Then I'll plug that back into where I solved the c. I'm going to take that and I'm going to bring it back up here, plug it into this equation here. And that gives me a new solution where the c is no longer unknown, 2x squared plus, and my c is ugly, natural log of 5 minus 2. And then to finish solving that, I'll make both sides exponents on e. And I'm going to tackle that plus or minus situation that we did at the end of 3 in this same step. I'm looking at my initial condition, and once again, my initial condition is greater than 0. So when I do e to the natural log of absolute y, I'm going to go ahead and drop the absolutes, and I know that I need the positive solution. So I'm just going to do e to the 2x squared plus natural log of 5, and there's the 5-year-old, minus 2. Okay, and I just got distracted. I think I was done. I think that was the end of the problem. I'm going to leave this like this. There is something you can do just to kind of let you know when you have a natural log in the exponent of an exponential like this, which we had in number 3 as well. You actually can. As a matter of fact, I think what I'm going to do is I'm just going to show you. No, I'm not. I'm just gonna stop here. I'm rambling and I'm distracted with children in the room and whatever. All right. So there's 4 examples, separable differential equations. Have a great weekend.